Welcome back, everybody, and welcome to this new session on with a start on project number 2. And I just wanted to discuss some potential variants, and depending on your interests, we can then dive into different topics for the lectures. So I was actually thinking today of discussing these Boltzmann machines and neural networks connected with project number 2. So that's one possibility. Now, the kind of options which we have, and you will find these under project number 2, is one is to just take project number 1 and replace the system of bosons with a system of fermions. And one of these systems is a system where you can use the harmonic oscillator, and it's called a quantum dot system. And these are electrons which are normally confined to live in two-dimensional regions, typically in layers between semiconductors. And it's a very hot system because people are using that as a platform for making quantum gates and for quantum computing. But it's also a system which is widely studied in condensed matter physics and in semiconductor physics. So this is a harmonic oscillator, but we will have to replace the interaction we had in project 1 with the Coulomb repulsion between electrons. So these electrons confined to move in a harmonic oscillator-like trap. These are called artificial atoms because they behave like a kind of atom. You have magic numbers. So you will have filled shells when you fill all the single particle states up to a given level. And then you require more energy to break a system, lose a particle where all particles fill up the shells or the single particle states, compared with you having an electron which is in a state which does not have another electron. So that if you think of helium, the helium atom, atomic helium, you have 2 electrons, and they are normally placed as an ansatz for the ground state in a spin up and spin down state in the lowest lying single particle state, which if we use the Niels Bohr way of labeling the states, it's called a 1s. Then if you go to atomic lithium, which has 3 electrons and 3 protons, then there's an electron which is now promoted into the 2s orbital, the orbital above. And in that case, this is an electron which you can rip off more easily, and the ionization energy is pretty small. So if you have a photon which impinges on atomic lithium, you can, with the right energies, you can knock out an electron. Whereas the 2 inner electrons, they are more difficult to knock out. It requires more energy. Quantum dots, they exhibit, and you can see that experimentally, the same kind of periodic structures which you have with the atomic periodic table. And they exhibit what's called magic numbers, etc., but in 2 dimensions. It's a very, from an academic point of view, an interesting system. And you can see that as a continuation of project 1, where you implement a fermion determinant in order to bake in the symmetries for fermions. So instead of having a wave function where till now we just looked at the products of single particle states, you now have to make an ansatz in terms of a so-called determinant or a Slater determinant. And that's a way to implement the antisymmetry, because for a system with spin half particles, the total wave function has to be antisymmetric. So what you're doing then is you're baking in the antisymmetry by hand by having a trial wave function which includes a determinant. That complicates things a little bit, but it's something which is fully doable as a continuation of project 1. Now, the other one, which allows you guys, if you're interested, since you're also following Physics 5429, both of you here, and also Alexander, who is not here now, this is actually to encode what's called Boltzmann machines in this course, and then look at neural networks in Physics 5429. But then you can hand in a unique report for both courses for the second project. So that's another option. But you can also do whatever you want in the other course and do either Boltzmann machines or neural networks here. But I would normally recommend doing Boltzmann machines. Now, parts 3 and 4 are more for people who have studied many body physics. And there are normally every year there are people who looked at Hartree-Fock theory. So that's a path by itself. And then we also have people who deal with quantum chemistry or more involved many-body methods who have been looking at something which is called copper cluster theory or more complicated many-body methods. So it's a little bit up to you what you want to do, but also if you have other suggestions, feel free to come with them. So give it a thought a little bit. And what I wanted to say more about is actually, I wanted to discuss a little bit about Boltzmann machines. And the reason for that is that this can give us a very easy continuation of Project 1. And the only thing which changes is the ansatz for the trial wave function. So what I'm going to do now is to give you a kind of a top-down view on it before we work out all the gritty-nitty details which are needed. And then you decide in a way what you find the most interesting case here for project number 2. And again, if you want to collaborate, keep the collaboration you had. This is a very good option. So what I wanted to say a little bit about now is, or dedicate the rest of the lecture, is how you can implement these Boltzmann machines, which have been a very popular so-called generative method in machine learning to quantum mechanical systems. And one of the reasons why I do this is also historical, because the first people to use them in quantum mechanical applications, that was a guy called Giuseppe Carleo and Troyer from, they were at the Technical University in Lausanne. And that was back in 2017. It was a paper in the journal Science, which really made a big impact in the community and laid the foundation for using neural networks in quantum mechanical studies and deep learning methods. Now, Boltzmann machines were also very popular, let's say in the beginning of the millennium, and also till roughly 2010, 2011, before convolutional neural networks really wiped them out as a competitor in imaging. But people use actually Boltzmann machines for imaging as well. Boltzmann machines have gotten a revival. And for those of you who've been following Physics 5429, these are normally part of a common denominator, which is called energy-based models. So you start with a probability distribution, and you make a model for the energy which comes into the probability distribution. And people have replaced an ansatz for the energy, which we will use here, which is a simpler one, simply because the project 2 is 5 credits. So there's a limit to how much we can do in 2 to 3 months, actually 2 months. And but people have replaced the kind of expressions we will deal with a convolutional neural network or a recurrent neural network. And that has given a revival to these energy-based models within the context of generative deep learning methods. Okay, so I'm going to switch over to the whiteboard, and we are going to look at some of the details which we would need to encode if we go for that. So let me just switch here. So the kind of general container for this is something which we will call generative machine learning methods. And the models which we are going to look at in particular are what is called energy-based models. And some of these are loosely also just known as Boltzmann machines. So also known as Boltzmann machines. but you don't need to do a Boltzmann machine. So the thing is that we want to train a probability distribution. So we want to train PDF probability distribution function, which I'm just going to label a P of X. And then we have a set of parameters. So theta are the parameters. And this is going to be given by some function E of minus beta and E. And if we use the Boltzmann distribution, it's just going to be, beta is just going to be the inverse temperature. But we are going to put that one to 1 because we're not going to use temperature. And then we have a partition function, which is a function of the parameters only. So ideally, a Boltzmann machine or an energy-based model is us optimizing a probability, argmin or max. So normally it's an argmax, but you can take the negative log. So the optimization problem is this one. So the optimal theta is then us optimizing this probability distribution. When we do that with neural networks, so a Boltzmann machine is actually a neural network. It's slightly different from what you're used to, but it is in principle a neural network. Now, if you now look at what we have here, since we are doing quantum mechanics, this changes life a little bit for us. So in standard Boltzmann machines, what you actually do is to take the derivative of this quantity to calculate the gradients. Actually, you calculate the log of this quantity, and you take the gradients, and then you optimize a probability distribution, which is trained on a data set. Now, when we apply this to quantum mechanical problems, we are a little bit more fortunate because we can now replace the probability distribution we had from project number 1, because now we are going to have a network. And we can think of this in 2 ways. One is a Boltzmann machine. And I'm going to explain to you what it looks like. So it's normally called a Boltzmann machine. The kind of machine we are going to look at is called a restricted Boltzmann machine. And this is normally shortened to RBM. So we are going to look at a restricted one. And I will use the acronym RBM, Restricted Boltzmann Machine. And I will come back to what that means. Now, the thing which is interesting for us now is that we know that we have psi, the trial wave function of x of the parameters theta, is actually proportional to this probability distribution of x as a function of the parameters theta. So we don't know what the probability distribution looks like, right? And what we are going to do now with an energy-based model is that we are going to use a Boltzmann machine as a trial wave function. Now, that is going to simplify life for us because the optimization now is an optimization where we now take everything we did in project number 1, but the only thing we do now is that we replace the wave function squared with a Boltzmann machine. And then the optimization is the same as before. So that means that what we want is to calculate the energy, expectation value of the local energy, as a function of x and theta. And we want to optimize the gradient. And we want to drive that one of this expectation value. We want to drive that one to 0. So that means that you can take everything you did in project 1. The only thing we need to do is to replace the trial wave function with a probability distribution, which now is going to look like this P of x of theta is now going to include some hidden parameters. it's going to be given by some P of X of H of theta. And that's going to be given by an E of minus E, which now depends on H and theta, divided by the partition function theta. And I'm going to explain to you what this H is pretty soon now, because this H are going to be parameters in a network. So you see now that we are making a model for the wave function based on a Boltzmann distribution. Now, the quantity where we are going to plug in all our training is actually into this quantity here. So we're going to make a model for that. And I'm going to show you different alternatives which are widely popular in the literature. This way of doing it is somewhat limited, because if you want to have a more advanced network here or some more advanced function, it becomes much more difficult to train and heavier to train. So one thing which people haven't done is to replace this one with a neural network. But we are going to make some simpler functional ansatz, which we are going to use for the training. And you will see that that is going to give us correct results if we have a harmonic oscillator with no interaction. But as soon as you bake in the interaction, this is going to give us something which is not as good as we would have expected. But this is something which is pretty straightforward to implement, and it leads to only small modifications in the program from project number 1. The other alternative, which is the one which often gives much better results, is instead of having a Boltzmann machine, what we do then is that we let a neural network and in this case, the neural network, which is going to be a function of X, this could be the positions of the particles and the parameters. The network is actually going to be our trial wave function. And that means that the probability we do, so in this specific case, although neural networks are seen as discriminative methods, in this case, we use a neural network as a generative method, because we generate actually the wave function by plugging in a neural network. And we know that then the probability distribution, which we obtain from the training, is then going to be proportional to the neural network. So let's call this NN of X of theta squared. So this is something for those of you who follow physics 5429. This could be one possible path for the second project. Then, if you do Boltzmann machines here, that means this part, then you can combine both of them, and you can do a critical analysis and set up the pros and cons of two different ways of solving a quantum mechanical problem with machine learning methods, but where essentially the machinery which you developed in project 1 is going to be almost untouched. The only thing you need to do now is to replace the trial wave function you had, which had only some few parameters, with a neural network which has many parameters. So typically, this recipe here, which you have, the optimization is again going to be, so if we now sneak in optimization here, optimization, yeah. We are still going to calculate the energy as a function of these parameters theta. And then we will also need the gradient with respect to the parameters theta of this expectation value. And this is exactly what you did in project number 1. So the algorithms you put up for the derivative of the energy is going to be the same. So you need to evaluate these free integrals with a Monte Carlo approach. But the only thing which changes now is that now these parameters theta is going to be a collective container for the weights of a neural network. And you can have many layers and the biases. So these are the weights and biases of a neural network. So in this course, I would normally, since you have a lot of machinery already, the simplest thing to implement is actually the first part. But when you've done that and you get familiarity with it, it's pretty easy to actually include a neural network. So this is a kind of a top-down approach to what we are going to implement. And if we now start looking at the Boltzmann machines, so if we think of a Boltzmann machine, if we do that, then so if we look more into the details of a Boltzmann machine and what we would need to encode, what we have is that we have a trial wave function psi of x, and these parameters h, which we put up, which are the so-called hidden layer parameters, they are parameters which we are going to define in just a few moments. So this is going to be given by some x of theta. This is a probability distribution. And we are going to write this in terms of an energy function to distinguish this from the local energy, because this is just a parameterization now. So this depends on x and theta. And then we have the famous partition function here. So this model, which we are setting up, model for a network, is actually this term E of x of theta, which then is going to be a function of parameters x or parameters h, which are called the hidden layer parameters. And then you have h theta as the parameters of the network. And the way this is going to look like is as follows. So it's going to be a network with one hidden layer. So the restricted RBM, a restricted Boltzmann machine, is one example of a typical Boltzmann machine. You can stack as many hidden layers as you want. But if you now look at the drawing which we can make of this system, it would look like as follows. So let's take a closer look at it here. So we could have some input nodes, which we call x1, x2, etc., up to some x of n. So this is what we will call the input layer. So this is the RBM. And then we have a hidden layer, which we put up here. Now, there's no problem in putting more hidden layers. So you can stack hidden layers on top of each other. Now, one of the things people saw is that the training became much more difficult then. So often a Boltzmann machine has just one hidden layer, and we will essentially just stay with that for the sake of simplicity. So we would have a hidden layer where we have hidden nodes. So we would have a hidden node 1, a hidden node 2, etc., up to some hidden node h of n. And then we have connections between the hidden nodes and the visible nodes. So these are connected. So we just write this connection with the arrows here. And same here and all over. So if you now think of this type of setup for a neural network, if you think of the input layer, suppose you have 10 particles in 2 dimensions. Then you need 20 input nodes. So one input node for every dimensionality and for every particle. So as I said, if you have 10 particles in 2 dimensions, m becomes 20. The number of hidden nodes is something you can use as a parameter. As I said, you can stack these hidden layers on top of each other. The restricted Boltzmann machine has also no connections between nodes in the same layer. So that's why it's also called a restricted Boltzmann machine. The original Boltzmann machines had also connections here, which means that you have more parameters to train. And that makes it more difficult to train. And in many, many cases in the beginning, people saw that it was almost impossible to train them because you had too many connections. If you have connections between the parameters here and here, internally between each layers, you get quickly many more parameters to train. So the simplest case we will be looking at is what is called a restricted Boltzmann machine. And that's the one we are going to implement, and we're going to make a model for this energy here. So if you now look at this model E here, so just keep in mind that this quantity which you see here, this one, this is not the energy of the system. This is the model we are going to make for the neural network. So if we now go back to this E tilde, this is now going to be a function of the visible nodes and the hidden nodes. And a typical model, and this is normally called a binary model. So we are going to call this a binary, which means that X takes only Xi, takes only values like 0 and 1, or -1, +1, etc. And same with the H of J, they take only values 0 and 1, only binary values. Now, if you now think of the harmonic oscillator, we know that the X's, which we have, are continuous variables. So this would definitely not be a good model for modeling project 1 with the harmonic particles in a harmonic oscillator which do not interact. But the typical model then, the binary, looks something like this. So we would have a sum of I equal 1 up to the number of visible nodes. There is a parameter AI multiplied with X of I. So these are called the biases. We have plus a similar one for the hidden layers. So we would have a parameter Bj times H of J, and then plus a sum of I and J up to M and N. And then I would have my X of I multiplied with Wij and multiplied with H of J. So these become then the weights which we want to train. And this is also a bias parameter. So that means that this theta is now a common container, is a container for the variables B, A, and W, A, and B. So these are the parameters which we want to optimize. So if you now have, suppose you have M equal to 10 and N equal to 10, that means that the A would be 10, that has a dimension 10. B has also the same dimension / length 10. And then we would have 10 input nodes, which are connected with 10 hidden nodes, which means that the number of weights must be 10 times 10. So that means that we would have 100 weights to parameterize. So in total, then we would have something like 120 parameters to parameterize. Now, this is a binary model. We would write this energy function in a more compact way because we can write this as in terms of matrix vector multiplications. So keep in mind that this is a scalar. It's just a number which we are returning. And that means that we can rewrite this in a more compact way. X of H and theta, which then becomes simply an A transposed times X. And now these are vectors, plus B transposed times H, plus X transposed times a matrix W times a vector H. So this will be the more compact way of setting this up. So that's a typical binary model. It doesn't need to be 0 and 1, but it could be -1, +1. It could be -2, +2, just two values. Okay? So you see now that when we are going to train such a network, if we have 10 particles in 2 dimensions, then X would have dimensionality or length 20. And then you can choose how many hidden layers, how many hidden nodes you want to have. So they just become parameters in the training here. So the code, which you will find at the end of the lecture notes this week, which we will also discuss next week, is an example of where we implement what's called a Gaussian binary model. So let's look at that model as well. So we have a Gaussian binary. So these are some of the most common choices for these models. And one reason for that is because the probability distributions, which we are going to calculate, they have simple analytical expressions, which then makes it easy to plug this into the optimization part. If you choose more complex functions, then obviously you have to do numerical derivatives. So one option here in project number 2, if you want to, you could replace these simpler models with a neural network, if you want to. And this is something which nobody has actually done. And it could even result in a nice research paper if we get interesting results, where one would compare a Boltzmann machine with a neural network and us replacing the trial wave function with just a neural network, as we discussed here. So you see the different paths we can take, right? But I would suggest that we look at a simpler Boltzmann machine in project 2 here. And then depending on how fast things move, we can actually add more complexity to it. And in particular, since many of you are following physics 5429 as well. So then we have the possibility of catching many birds with just one stone. So a Gaussian binary model for this energy function, or E tilde, it's not an energy. So this should not be a semicolon. So this is X and H, and this is a semicolon. So a Gaussian binary would be a model which can look like this. So we still sum over 1 up to n, m, and then we could now have an x of I minus some a of I squared, and we can have a division by some constants, which in this case could be, let's say, a variance, but it's normally put to 1. So it could be a sigma I squared. And you see now that if you think in terms of the harmonic oscillator, you're getting a trial wave function. Since the trial wave function is now the probability, trial wave function squared, then we will have something which looks like a harmonic oscillator. So if you think back of the harmonic oscillator, the trial wave function is e to the minus alpha times x squared. So this term which you see here, when we plug that one into the Boltzmann distribution, it gives us something which looks like a harmonic oscillator. So a Gaussian binary contains more terms, obviously. So we will have the hidden nodes. So the x's are now continuous variables. So these are continuous. And then I have a sum over the hidden layers. So you have these parameters which need to be trained by the network, plus, and then I have all my terms, I equal 1 up to m, and j equal 1 up to n, and then I have my x of I times, so this continues here, times ij times h of j. So when you train your Boltzmann machine and you use a binary, you will often see that your results are not going to be very good. If you do a Gaussian binary and you don't include any Jastrow factor and you just look at a non-interacting case, the fact that you have a function here which looks like a harmonic oscillator, and if you have a harmonic oscillator problem, is going to give you something which is pretty close to the exact value. Actually, if you run the code, which we have in the end of the Jupyter notebook this week, you will see that this actually gives us the exact value. Okay? Any questions so far? Does it sound, I mean, I'm trying to give you the overarching ideas of what we are going to do. So we will, in the project here, the kind of system we will focus on, or model which we'll focus on, is actually this one here. So that means that the h's, they take only values like 0 and 1, or -1 and +1, whereas the x's can then just be randomly distributed according to a Gaussian distribution. And then you would simply then generate this model. You would train it with the parameters theta, and the training involves you calculating the gradient of the energy. So the only difference now is that your trial wave function is not going to look like a harmonic oscillator times something, but it's going to be given by something which runs like this. And where the parameters then are many more than you are used to from project one. But essentially what you end up doing is very, very similar to what you did in project one. So what we need to look at now are several technicalities. And let's go through these technicalities, because you will see also that type of equations we end up having to program actually pretty simple if we stay with a Gaussian binary. Similarly, if you have a binary, it's pretty simple. You see also that you can make this more complicated. You can have a Gaussian, or you can have binary Gaussian if you want to. If you have a Gaussian, you can still calculate these probabilities analytically. So the thing which is nice with these simpler models is that when we are setting up this quantity, which we will need, because in our case, this quantity is going to be the wave function squared. So that's the one we are going to plug in when we do the variational Monte Carlo calculation. And with a simpler function like this, the thing we need to do now is to integrate away these degrees of freedom. So let's look at these details, because that gives us something which in statistics is called the marginal probability. So the hidden layers which we have, they are used in the training. They give us more freedom to explore the best possible representation of the states. However, when we look at the final result, we are only interested in a probability which depends on x, because the hidden layers are just additional parameters which are not of interest for the final wave function. Okay? So let's go through some of these technicalities which lead us essentially to some basic statistics. Okay? So let's just set this up as technicalities, because that's what we need to do now. Now, if you look at the partition function which we put up, this is a function of h and x and these parameters theta. And since we use the Boltzmann distribution, it's going to be given, and we put this beta, the inverse temperature, we just put that one to 1. And now I'm going to drop the tilde term, if that's okay. So now I'm just staying within the context of a Boltzmann machine. Now, the C of theta is what we call a normalization factor. If you take a course in statistical mechanics, this is called the partition function. So this is a normalization factor, like we had the normalization factor for the trial wave function. Or if you go into statistical mechanics, this is called the partition function. So if we now think of this z, so z is going to be a function of the parameters theta only. This is something which creates some problems in the optimization. And what saves the day for us is that we are not going to optimize a probability distribution, but we are going to optimize the energy. So if you go into the field of generative methods, and in particular Boltzmann machines, what you will see then is that you need to deal with the derivative of this quantity here. And this quantity is actually, from a computational point of view, it's actually the nasty quantity, because this has an infinity of degrees of freedom. So if you have a continuous distribution, this will be an integral over x, where x is defined over a domain. It will be an integral over the d of h, where h is now into another domain, which we can call for E. No, not E, we can call it for F. Or let's just call it for a D prime, which is much better because then it refers to the letter D for domain. and then we have an integral over h, and then we have an e of minus beta. Let's take away beta. We decided to take that one away. Of e of x of h of theta. Alternatively, if these are discrete variables, which we normally end up doing, this is a sum over I or xi in a specific domain is a sum over hj defined within a specific domain, and then we have an e of minus e of xi of hj as a function of the parameters theta. So this is the partition function itself, and you see quickly now that suppose now that you have a binary case. Just to give you an example. And you will see quickly why this explodes. Example, if we take a binary case, then what we have then, we can take as an example, suppose m is equal to, let's just take a number here, which is 10. And then we do n equal to 10. That means in each case here, the sums over xi is actually equal to 2 up to the power of m, which in this case is 1024. And similarly, in this case as well, we get 2 to the n possible states, which you can reach in a binary case. So this is actually a very small case. If you think of something like the Ising model in statistical mechanics, then this m in actual calculations can be in the thousands. But you see now that even here, you would now have 1024 x values and 1024 h values, which is already a pretty large number. And this is a very small case. So that means that calculating this quantity here becomes quickly very involved. And this is, in our case, we are a little bit fortunate because this disappears in the calculations which we're going to run. So we don't need to evaluate this quantity. If you, on the other hand, if you're not optimizing the energy, but you're optimizing the probability as you would do in a normal generative model, then we have to look at the derivative of this quantity as well. And that becomes a little bit more tricky. Okay, so the thing which we want, what we want in the calculations is the marginal probability. So we want a trial wave function of x of these parameters theta, which are proportional to this probability p of x, but without h. And this is called, this quantity which you see here, is called the marginal probability. So this is the quantity which we actually want to have when we are going to set up the calculations. So in our specific case, what we want then is some p of x of I, a specific configuration, which is now a function where we have summed out because we're going to deal with discrete quantities. So that means that we have an x of I, h of j, and as a function of theta. So if we now go back to what we had in project one, so let's take a closer look at what we had here. But in essence, in project one, what we did was to optimize this quantity, but then we had only one parameter, which we call for alpha. That was essentially what we did in project one. So let's look at how this links with what we developed in project number one. So the question then is, how can we use project one in project two with Boltzmann machines? Then it fits to take a small break. So what I wanted to do now is to give you a short, how to say, repetition of some basic concepts from statistics, which we will need in order to get a better understanding of what is going on. So if we look at the standard Boltzmann machine, without thinking of the optimization problem which we have, because we are going to optimize the energy, but the standard Boltzmann machine optimization deals with you optimizing the probability distribution. We discussed some of these topics last week in Physics 5429. So let me bring back these topics here. So if we now look at if we just write down the probability distribution before we answer this question here. So let's now set up an intermezzo. And this deals with the standard Boltzmann machine approach, BM approach, or energy-based model approach. So what we have is a probability distribution. If we now assume that we have independent and identically distributed events, then we can make an ansatz for this probability distribution Px of h, where this is now given by all the possible probabilities which we have. And these probabilities are now given by all the possible outcomes, hj, sorry, equal to 1, and up to n. And then we have the individual probability P of x, of h of j, and of theta. So we are assuming that all these events are now independent and identically distributed. So it means that there is the same probability distribution. So the total probability is just a product of the individual probabilities. Now, if you think back to what you did in project 1, when you didn't have an interaction, the wave function was just the product of the single particle wave functions, which were just harmonic oscillators. And that would be an example of a similar probability distribution where all the objects are independent of each other and identically distributed. So if you assume that, the standard approach is that we now take the optimization of this quantity here. So we are not going to optimize the product, but we are going to optimize the log of the probability distribution. And then we are going to optimize this with respect to all the parameters which we have. So we could now say that there is a set of parameters P which we need to optimize. And then we typically optimize log of P, of X, of H, of theta. That's the typical approach which we would have when we are doing this in a standard Boltzmann machine-like approach. Now, the thing we are interested in is actually the marginal distribution. So let me just bring up some of these elements. So we are in general interested not in the probability in terms of h and x, but we are interested in the marginal probabilities. So that means that we are going to have a probability over x. Now, in our Boltzmann machine, we will actually need the probability of h as well. But the one which we typically want to set up would be this one, where we now have an x, and an h of j, and theta. In the Boltzmann machine, and I'm just setting up this for the sake of completeness, we will need this quantity here as well, because we are going to set up a set of calculations where we need to find the probability of the visible node and the hidden nodes. And then we need the probability of a hidden node when we have summed over all the visible nodes and vice versa. So that's just going to be a sum over all the xi's which we have and I have an xi, and this is going to be h. So h now and x could just be one single one, or it could be all of the h and x values. So these are normally what we call the marginal probabilities. And then we also have something which is called the conditional probabilities. So let me just list them. And the conditional probabilities are then given as x as a function of a given h. So this bar means that what is the probability of x given h? And since we are carrying with us all these parameters, we need to have that one as well. And from statistics, this is the same as the probability h of theta of x divided by h. This is the marginal probability. And then we have the conditional probability for h given x with the parameters theta. And that is obviously p of x of h as a function of theta, but now divided by p of x with the parameters theta. So these are quantities which you may have encountered when you look at the course in statistics. So the thing which we want to optimize is actually, we don't want to optimize this quantity here, but we want to optimize the marginal probability. Because at the end, the visible variables are those which are of interest for us. So we want to optimize the quantity p of x of theta, which then is actually going to be given by some 1 over c of theta, the partition function, which is just a normalization constant. And this is now given by some I x of I, element in the domain of events where x lives. And then it's an f, a function x of I, f of x, where this f of x of I is typically now, in our case, given by e to the minus e of some x of I of theta divided by, actually it's only given by that function there. So let's just keep that one as it stands here, like that. So the optimal parameter theta, which you would get in a standard Boltzmann machine approach, is that you take the maximization of the log of this quantity here. For all the theta, which are now elements in this domain of theta values. And that means simply that we need the d of log of p of x of theta, and we want that one to be 0. So that's the optimization problem, which you would typically deal with in a standard Boltzmann machine. Now, this quantity here is something which we can rewrite, and I'm just going to set this up, the final expression. For those of you who are following Physics 5429, we went more thoroughly through the derivation last week. But what we end up with then is a function. So this derivative, which we need to set up, is the derivative of d of theta. And then we are going to have a sum over the xi values of log of this function f of x of I with respect to theta minus, but then we have the expectation value of the derivative of log of f of x of I. And we want that one to be equal to 0. So the first quantity is something which we can calculate when we have this model here. So if somebody now gives us a Boltzmann machine, just to give you an example, if we have a binary, what that one is given by this expression here. And then we would have 1 over z of theta. And this is multiplied with E of A transpose times X. And then we have the product over all the J values, which go up to the number of nodes which we have, of 1 plus E of Bj plus X. Let me just put that one in here. X transpose times W. And this is now multiplied with the values of J here. So I'm just putting this up because it's this function originally, if we now look at the original function, this f of x of I, of h of j, of theta, that is given by a function a of t of x plus b transposed times h plus x transposed times w times h. So this kind of strange notation which you see here is us taking the derivative with respect to a given component. Now we're summing over a specific component over h of j here. And we are summing over all the hj values. So this quantity here is now the quantity which we need to look at when we want to perform the optimization in here. So the probability distribution when we have this function is something which we would have to put in here. And then we need to calculate that expectation value. So this will be a typical binary probability distribution, which we want to optimize with respect to the parameters. So the terms which you see here now, these specific terms, they would enter this calculation, and they would also enter this expectation value. So that's an expectation value which we have. This is the standard way by which you would do a Boltzmann machine. Now, we are not going to optimize the probability distribution, but we are going to optimize the energy. So in our case, what we will be optimizing is actually the energy. So we are going to minimize the energy. And this is the quantity which we need to set up. And in our case, this is going to be given by, if we have a continuous distribution, by P of d of x of P of x of theta multiplied with the local energy of x of theta. And that means that when we now calculate the derivatives for a given specific parameter, so we are going to take this quantity here of E of xj as a function, sorry, x as a function of theta. We want that one to be 0. So if we look at a specific parameter of E, so one of these of the many parameters is going to be given by this integral, which we have evaluated before. So we have the local energy multiplied with 1 over psi of t of d psi t of d theta I. That is one of the expectation value, which we have already set up in the program in project 1. The expectation value of the local energy, and then the expectation value of 1 over psi of t of d of psi t of d theta I. So the only thing which we need to look at is the encoding of the new wave function. And we also need to obviously have a new expression for the local energy based on a new trial wave function. So if we do everything with automatic differentiation, like with JAX or something like that, then it's much, much easier. But we can also set up, for some of the simpler cases, we can set up analytical expressions for the local energy. So in our case, when we now look at these type of calculations, let's look at some of the details which we would need to implement now. So one thing we will need is this quantity here, the trial function of d of psi of t of d of theta of I. And that is obviously given by d of ln of psi of t of d theta y. So what we are going now to set up as a parameter for this energy function, or this model. So the model in the restricted Boltzmann machine, which we will carry with us, is now going to be given by this E tilde of x of h of theta. And we are going to train a neural network where we now have a sum from I equal 1 up to m. And we are going to look at the Gaussian binary. And then we have divided by some variance, which we normally are just going to put equal to 1 because we don't have that function. X of I, wij of h of j. So the parameters which we need to train now are this one, and that one. So these are the parameters. And we are going to assume that the AX is a continuous variable, although we are going to run with discrete calculations anyway. And the H's, these ones, they are given by a binary set of values, which means 0, 1, just 1, 1, minus 1, 1, etc. So if we now look at the trial wave function, which we are going to have, then if we look more closely at it, the standard assumption now is that the trial wave function is going now to be given by this marginal probability. And we are going to put that one equal to e to the minus e tilde of x of theta. So we are integrating away these parameters h. And this is simply the marginal probability which we put up. But the difference from a standard Boltzmann machine with what we are going to do now is simply that we have a optimization problem, which is an optimization of the energy itself. So it's the Hamiltonian of the system which is going to drive the optimization part. And that's a big difference from a standard Boltzmann machine. So what happens in our case then is that the trial wave function psi of t of x of theta, that people have tried with different possibilities, is actually to set this equal to the square root. We are going to assume that we have, and with a harmonic oscillator case, which we will be looking at, we are going to have real wave functions only. We're going to look mainly at the ground state. And this is going to be equal to 1 over the square root of z. And I just write c instead of writing c of theta. And we are going to have a sum here where we now sum over the variables h of j. So this h of j take values. They could be -1 or 1, or if you prefer, 0 and 1. It just changes slightly the expressions. And then we have e to the minus of this model e of x of hj, and then as a function of theta. So that is going to be the trial wave function, which we will be using. Alternatively, you could just put the wave function equal to the probability. But it's pretty common to actually use the choice which we have set up here. So if you now look at the trial wave function, if you do the mathematics now, what you will see is that this ln of psi of t of x of theta is going to be equal to minus 1/2 of ln z. And I'm dropping this dependence on on the parameters theta. And then I'm going to have a 1 over n up to n. And then I have my xi minus a of I. So the nice thing with having an exponential here is that life becomes much easier. And then we would get a plus 1/2. And now I have a sum over j equal to 1 up to n. And this is an ln of 1 plus e of bj plus. And then I have a new sum here, which goes like I equal 1 up to m. And then I have my x of I of wij. So what I've done here is actually to sum away the parameters h of j. And that's why we don't have h of j anymore here. So this 1 here comes from the point where h of j is equal to 0. And then you have the other case, which gives you 1. So that's why you have b of j here. Okay, so this is just me setting in the wave functions. And in the optimization, what we need the following terms. We need a d of ln of psi of t with respect to a of I. We need a dln of psi of t with respect to bj. And finally, we need the derivative with respect to the weights wij. So when we now are setting up the final optimization problem, we then need actually to set up these quantities here. Okay. So then the next thing which we need to think of is actually the way the local energy is going to look like, because that will introduce new additional features which we need to encode here. So as I said, I mean, you can use JAX to set up the derivatives and use automatic differentiation, because you are going to have operations on simple functions like the logs, the exponentials, etc. But you see, one of the advantages of having everything in terms of this ln here is you see quickly now that these terms become much, much easier to calculate, actually. So let's now look at the next thing which we need to think of. So the Hamiltonian, in this specific case, we're going to look at the harmonic oscillator case with an interaction. So this is going to be given by 1 up I equal 1 up to n, the number of particles which we have. We are going to have a kinetic energy term plus 1/2. And then we have the harmonic oscillator as before of an Ri squared. And then we have an interaction piece where we have an interaction V of Rij. And this interaction, this Rij, is just the relative distance between two vectors, which is nothing but this expression here. If you're in 2 dimensions, it's xi minus xj squared plus yi minus yj squared. So when we look at the local energy, this is also something which comes to our rescue here, because everything gets a little bit simpler, because we are going to have a local energy, which we know is given by 1 over psi of t, and then we have h times psi of t. Now, since we have this specific form for the wave function in terms of this logarithm, what we will get then when we do the math here is that we get 1/2. This is a kinetic energy term of I equal 1 up to n. And then we are going to get a minus, and we will have a d ln psi of t of dx I this is squared, minus, and then I have the next term, which is a d second derivative of d of xi of ln psi of t. So this is a kinetic energy term, and that's the one which causes problems for us. And then the next term is just the harmonic oscillator part plus the energy itself, because the harmonic oscillator part, which we have here, does not change the wave function. So that means that I can just take this sum here and this sum here. So that means that we do have a plus here, which comes in plus, and then I have a factor of 1/2, and then there's a sum from I equal 1 up to the number of particles, omega squared or I squared, plus an I less than J, and this is up to the number of particles of this potential which we have, Rij, like that. So these are the equations which we need to think of when we now are going to set up our Boltzmann machine. Okay, any questions so far? So let's now look at the explicit Boltzmann machine here, and we are going to take one of these models. So if we now let us now look at an example and how we can do the calculations. In the lecture notes, you will find the calculations of a binary and a Gaussian binary Boltzmann machine. So let's now go through the binary case, because that's the simplest one, and just go through the mathematics which we need. So this function which we have is of x, and I'm going to simplify it a little bit. So I'm just going to write this as an e tilde of x of h. I'm just going to skip the theta because the parameters will just appear immediately here. So what I'm getting then, if I look at this function, is that this is given by some at of x plus the b transpose times h plus x transpose times the matrix with the weights times h. And I'm going to use a binary case. So that means that x of i's, which we have, take values between 0 and 1. And the h of j takes values 0 to 1. So if I look at the partition function as a function of theta only, that is going to be given by a sum over x and h. And it's going to be a e. And now I have a sign here because I have a minus sign in front of this quantity. So it's an at of x plus a bt of h plus an x transpose of wh, like that. So let's continue a little bit with the details here. So what we have is now a term which we want to optimize, and this is the quantity which is the marginal probability. So we are going to have something which is given by z of t. And now I'm just going to make a small change here. I'm going to assume that this e has a negative sign. So I'm just going to put a plus here. So just put a minus. No, not a minus here, it's a plus, but a minus of this function. And let's now look at the quantity we want to optimize. So this is an e of at of x plus a b of t of h plus x transpose times omega times h. Now, if we are summing over h here, this means that we can rewrite this one as an e of a to the tx divided by c of t. And then I have a sum over these binary values. And this is going to be given by e of b of t of h plus x transpose of w times h. I can then rewrite this now because these are summations which I need to deal with. So I will now have a sum over the hidden nodes. So this is going to be given by E of A transpose times X divided by C of theta. And then I have a sum over H here. And then I have E, and then a sum over the hidden nodes. So this is for every H, I have a specific hidden set of hidden nodes. And this is given by 1 up to n. And then I have my Bj plus, and then I have my X transpose. And now what I'm doing is actually to suppress the multiplication with X and T, because X transpose times W becomes a vector. So this is a kind of compact notation for the multiplication of X transpose times W and giving us a vector, which is then ultimately multiplied with, so this has a component J here, and this is multiplied with H of J. So this strange notation here with the asterisk, that means that I'm performing a multiplication over all the rows, no, the columns, which refer to the same indices as X of X transpose. Now, this is now something which we can rewrite in the following way. T, and I can rewrite this as a product over J equal 1 up to N. And then I have my E of Bj plus my X transpose. And then I'm performing this multiplication with a vector times the corresponding columns in the matrix W, no, rows J, and this is multiplied with H of J. And if I then plug in the values here, I can actually rewrite this one in the following way. So let's just do that. So this is going to be equal to 1 over Z of theta multiplied with E of A of T of X. And now I can now single out the different hidden nodes. So I have an H of 1, which is either 0 or 1. And then I have my E of B1 plus X transpose times W component 1 multiplied with H of 1. This is then multiplied with the next one, which is an H2 equal to 0 and 1. And then I have my E of B2 times H2. And this goes all the way down to the final one, which is now given by, obviously, H of N is equal to 0 and 1. And then I have my E of B of N plus X transpose times W. And then I have my N value multiplied with H of N. So if you look at these terms which you have here, these can be summed independently of the other ones. And you see now that you have a term where you have Hn or H of I equal to 0. So that means that when it's equal to 0 here, then this term here just gives us 1. And then I have the next term, which is then when I put in 1 here, you can quickly see that what this gives us, if you look at, let's say, this term here, that gives us E to the B of N, 1 plus E to B of N plus X, sorry, E to the B of N, it should be written like this. So this is argument, and then I have X transpose multiplied with the matrix W, but where I keep column N here. So in that way, I can now collect all these terms and then find the final expression, because what I get here now is simply the product of all these different terms here. Okay. Now, we can now repeat this exercise for the h's, and then we can find the final probabilities, which we will need to plug in when we now are going to compute the derivatives. So what I want to do now is actually, instead of going through all these calculations, because this is not so exciting, I'm going to list the expressions which you will get, and also the expressions you will get when you change this to a Gaussian binary. But the basic exercise, which we need to do now, when we are going to calculate derivatives, is actually to set up these probabilities. We need the marginal probability. And this is the quantity, if you look at this one, this is the quantity which now defines the trial wave function which we have put in here. So when we are going to calculate these logarithms, then for the type of Boltzmann machine we have, we need to plug in these different analytical expressions. So you see the basics? So this is not too exciting. So if I were to go through the binary case in full detail, the Gaussian binary case in full detail, we would spend some 2 to 3 hours by just doing some integration and algebras and multiplications. So let's look at the expressions which we end up with by going back to the Jupyter notebook. So in the Jupyter notebook at the very end, you will also find a code example. But let's now try to look at the expressions which we need to plug in. And when you look at these different calculations, it's not the most exciting case, but you will first find the binary case. So let's just look at all these expressions. So the probability which you have, so with this kind of function, this is the probability you get, the binary case. And it looks like this. Then the partition function is just the sum here. And we want the marginal probability where I've skipped the parameters, the different parameters. So the marginal probability is the one which we just calculated. And this is the expressions which follow now. And we rewrite it in this compact way. And we end up with this expression. And then we then set in the values for h of 0 and 1. We get this expression. So that is one probability. Now, when we are calculating the probability of the outcome from a hidden mode, we need also the hidden marginal probability. So this is an exercise here, which is exactly the same as before. So then we can get that quantity. You can see that this is almost equal to the one which we get for the visible layer. We will also need quantities like the conditional probabilities. So this is just the total probability divided by this one. And you can actually show that these take simpler expressions like these. And then we find the probability of a hidden unit being on or off. Because when we are setting up the training, we need to find whether it's on, given a value for x. And we need to find it whether it's off with a given value for x. And these are quantities which we can derive analytically. Now, these derivations here were made because, and these simpler models, because you could get analytical expressions for the probabilities, which you then can use in the training of the network. But now with software like JAX, this is something which you can do automatically. And this gives you much more flexibility to play around with different types of probability distributions. So in the code examples, I've actually tried to follow this kind of basic analytical machinery, but this is not the way we would do it nowadays with efficient libraries for automatic differentiation. So, but just keep in mind that the historical background is simply because you can calculate easily the different analytical expressions. So you can calculate the probability of x given being 1, given a given value for h. And these are things which we will need to set up in the calculations. Then comes the next one, which is the Gaussian binary, which is the one which is implemented in the program. And in this case here, you can actually set up the joint probability. So you have a new partition function, and you can perform the same calculations as before. But now you need to set up the marginal probability for X, which then, after some exciting exercises, gives you this expression. And then you can do the same thing for H. So it's, as you can see here, it's not the most exciting exercise. And I think you wouldn't be too excited if we went through all these details. So these are just specific details, which then, when we have all these elements, we can then go back to the neural quantum state. And what we are simply going to say now is that our wave function is given by this quantity here. Some people have played around with taking the wave function itself, given by the Boltzmann distribution. That introduces essentially a factor of a half when you look at the log of these quantities. So this is a quantity we end up setting up. So this is our trial wave function, which you can see here, where we now are summing over all the hidden nodes. So this is the trial wave functions you end up with. Then the nice thing, when you now are dealing with the local energy here, which is the quantity we want to take the derivative of, since this contains the wave function here, and it has a normalization constant, you see that the normalization constant disappears. So we don't need, when we optimize the energy, because the wave function now has a 1 over the square root of z. It has a 1 over square root of z here, and z is just a constant. So when you calculate the kinetic energy, this is just a constant, which is divided by the same constant. So the standard Boltzmann machine, which we discussed before, forces you to actually calculate the derivative of the partition function with respect to the optimization parameters. But since we are optimizing the energy, we then have the wave function here, and then the wave function in the denominator, and that takes away the partition function. So in a way, this doesn't appear in the calculations. It makes life much easier when we set up the Monte Carlo machinery. So at the end, we don't need to worry about this quantity, which is actually the nasty quantity. And at the end, we end up setting up these expressions. And what you will find here are the derivatives with respect to the different parameters, which we need to calculate. So we do have this here, and then these are the different expressions which I have encoded here. So next week, I wanted to go through some of these details and then discuss the code as well. And as I wrote in the email to you guys, the plan now is to discuss this program and then look at how we can implement it in the codes, so that before we take the Easter break, we have all the machinery which is needed to implement a Gaussian binary Boltzmann machine. And you have already a skeleton for a program here. So next week, we are going to go through more of these details, which you see here, which we now haven't dealt with. And then we are going to look at how we can encode this. So I hope this tour here, which we had today, gives you the overarching ideas.